Good morning. We are moving on today into chapter 24. This is a big moment because for 3 chapters now, 21, 22, 23, we have been discussing kind of a foundational understanding of electric charges, electric forces, electric fields, electric potential energy, and then looking at some really detailed problems as to how they're all related. Now we're kind of switching over. We're going to take much of what we've learned, a good portion of that, and we're going to use this to start analyzing different devices, devices that we could use in an electric circuit. And so what we're going to start off with in chapter 24 is something that we call capacitors. I see that's not in the title. So these devices here are called capacitors. Capacitors store electric charge. They're actually able to store a certain amount of charge within the device. We've said that that's not a common thing that happens, but capacitors are able to do that. Now what they're saying the chapter deals with is electric energy storage, okay? Capacitance, that's a property that these devices have. Dielectrics, we'll talk about that too, but the big focus here is on capacitors. How much capacitance do they have, and how much energy are they able to store? Now, yeah, these are all examples of capacitors. You may see these if you open up some circuitry of that's lying around. Look around your apartment or your home or whatever and see if you can track down some capacitors. Capacitors, here we go. So a capacitor is a device. It's pretty simple. It consists of 2 layers of conducting material. And they're not allowed to touch. Now in actual practical capacitors, the way that they're not allowed to touch is we put a layer of insulating material between them. But for right now, we're going to ignore that effect. We'll come back and talk about the effect of the insulating material. So right now, we're going to treat this as I've got 2 pieces of conducting material, and they do have the insulator here, right? So here are these layers of conductive material, and we're going to charge one of these to be positive and negative. So in this capacitor that they're actually building, alternating layers would either be storing positive or negative charge as we kind of switch back and forth. Now, the capacitors are built, most capacitors are built, so that at least to some extent you can reverse the charge. Some capacitors are designed so they're designed to have the positive charge on one plate and the negative on the other, but for the most part, for our purposes, we're going to treat this as kind of interchangeable. All right, now the properties here that we're going to be interested in is how much charge can these things store. So we're going to say on one of the plates we're going to be storing an amount positive Q, and at the same time on the other layer of material we'll be storing negative Q. So the positive and negative Q's balance, and in fact we can see that the amount of positive Q we get on one side, the amount of negative Q on the other, they match in a capacitor. So we'll see how that works. And then there are wires that are attached here. Notice I have a wire attached here and a wire attached here. You can see the wires over here to the 2 layers. And that's going to allow electrons, say, coming into this side will make it negative. Electrons pulled away from that plate will leave that positive. We're interested in what are the cross-sectional areas and how much separation is there between the plates. So that's what the capacitance is going to depend on. Here's another very nice diagram. Oh my gosh, it's a battery. So such a practical device. We've been looking at all these electric fields and electric forces, and now we actually get to look at something like, hey, it's a battery. It's got a positive terminal, it's got a negative terminal. Now you might think, hey, don't batteries store charge? And they don't. What batteries do is they run chemical reactions, and during the time that the chemical reactions are running, charges are pumped through the battery or through the circuit. So what's happening here is, let's disconnect the battery at first. So I got this battery here, it's not connected to anything. It's got a bunch of chemical reagents inside, but the reaction's not running. And that's because there's really nowhere for the electrons that are going to be moved in these reactions. So the chemical reactions actually are able to take electrons from one location, move them to another, but there's no completed path. So what we have to do when we build an electric circuit is we have to provide a path along which electrons are able to transfer. And so once we connect the battery to this path, the electrons are able to begin to move. And that means that the chemical reactions then can continue. If the chemical reactions try moving the electrons and they don't go anywhere, which is what happens when the battery is switched off, then the reaction shuts down pretty quickly. You build up some electrons on the negative terminal and you deplete a few on the positive, but it doesn't go very far. Once the electrons are allowed to flow through, then the chemical reaction proceeds. So now in this case with a capacitor, this is a capacitor that we've built right here, and that says that, well, here's the negative terminal, and those electrons are being pushed through here. Now, an important thing to remember with electric circuits is, in order to charge this capacitor, do I have to wait for electrons from the battery to reach the capacitor? And I don't. Electrons are everywhere in the circuit. So even before we attach the battery, there are electrons everywhere along here. And there are electrons everywhere along here. When I close the switch, what happens is electrons leave the chemical reactions inside the battery, and other electrons are drawn in through the positive terminal. And what that does is it makes all the electrons through the rest of the loop go into motion. Along the way, we'll end up doing some calculations to get an idea of how fast electrons are moving typically. And what we find out is the electrons are moving really, really, really slow. They are not moving fast. So most of the time when we're using a battery or even when we're plugging something into an outlet, the electrons are not moving especially fast. It's the fact that the electrons are everywhere. And so when we turn the circuits on, the electrons start to move. Now, what will happen with this battery is electrons that were right here are going to move onto the capacitor. So it's the nearby electrons that begin filling up the capacitor, and then all the other electrons just take one step farther and another step farther. So every time the electrons take a step forward, there's going to be some waiting in line here, and they're going to jump onto the capacitor. Those are the electrons that are going to charge that negative plate. Similarly, at the positive plate, when these electrons step away from the positive plate, that allows electrons from the plate itself to move into those vacant regions. Okay, and now what's pumping this whole thing? It's the battery. The chemical reaction of the battery keeps pulling electrons in from this terminal and pumping electrons out through the other terminal. So batteries don't store charge, they pump charge. They keep the charges moving, but the battery itself remains electrically neutral. That's not true with the capacitor plates. The capacitor plate, there's a negative plate and a positive plate. The capacitor plates become negatively and positively charged, and that's why we say capacitors actually store charge. Now you might say, because the negative charge buildup and the positive charge buildup is the same amount, the capacitor overall remains electrically neutral also. Yeah, that's true. But because we've got negative charge isolated from the positive charge, we're able to add to that negative charge or pull some of that negative charge out. So it does become a charge reservoir for the rest of the circuit. Now, in terms of symbolically, a circuit like this looks like the symbol for a battery are two parallel lines. The symbol for a capacitor are two parallel lines. Whose idea was this? Okay, so the capacitor, the two parallel lines represent the two plates, and for a capacitor they're drawn to be the same length. For the battery, the plates represent the surfaces on which the chemical reactions are taking place. But what we've done is we've agreed on a convention where the negative terminal is a shorter plate, the positive terminal is shown as a larger line. So anyway, symbolically, don't get them mixed up. The capacitor has a property of capacitance. The batteries, we're going to find out, and we've talked about this in chapter 23, batteries have a property of electric potential. Okay, so they're measured in volts, and that's related to how much energy per charge those electrons will have when they're being pumped through the battery. So the battery provides a certain amount of energy per charge for every electron that gets pumped through there. So that property is voltage or electric potential, and the capacitor's property is capacitance. All right. More of the same. So this is my own diagram of what we just looked at. This is to try and drive home that point of where are the electrons coming from? Well, the electrons are in all the chemical reagents in the battery. The electrons are everywhere inside these copper wires, for example. And so what happens is when we turn this circuit on, all the electrons move. It's not that we're waiting for the electrons to travel through the circuit. All the electrons, essentially we treat this as it happens instantaneously. There's a tiny time delay, but for us right now it's small enough that we say as soon as we turn on that switch, all the electrons immediately go into motion. And so as soon as we close the switch, the electrons that were in the wires over here are able to jump onto the plate. The electrons that were on this plate are able to jump off and fill in these regions where these electrons have started to go into motion. Now what's kind of interesting with a capacitor is there's actually a gap in the circuit. So electrons don't cross from this plate to this plate. They don't cross from one side of the capacitor to the other. All the other devices we look at with circuits, the electrons are going to be making their way through that device. The battery's the same way. Electrons are going to get drawn in. They're going to be involved in a chemical reaction, and electrons are going to get released from the chemical reaction. So we can think of those electrons as kind of making their way through the battery slowly. But for capacitors, that's not the case. So batteries pump charge, capacitors store charge. Chemical reactions in the battery are what enable the battery to move charges along. Now, a very useful analogy for the motion of electrons inside a circuit is to treat the electrons as if they are a non-compressible fluid. So electrons repel each other, and that means if one electron moves a little bit in this direction, all the other electrons in this direction get pushed. And then the electrons in front of them get pushed. So everybody is getting pushed at the same time. It's very difficult to bunch electrons together. You don't tend to get accumulation because the repulsive forces between electrons are so large. And so it's kind of like, well, the non-compressible fluid could also be thought of as a series of blocks. If you want to go back to chapters 4 and 5, what we could do is we could get a bunch of blocks, put them on a surface with friction, so the surface has friction to it, and we'll write the symbol electron on each one of the blocks. Now what happens is if I start pushing on this block, all the other blocks move. So if the battery is located here, and the battery is pushing electrons forward, it ends up moving all the electrons in the circuit because they're like blocks. And one electron will push on its neighbors, and everybody throughout the entire circuit will go into motion. So this is kind of our first look at electric circuits, and this is a really fundamental idea conceptually, thinking about what's going on inside an electric circuit. So again, I don't have to wait for the electrons to show up. As soon as we close the switch, the motion of the electrons, the electric current, happens everywhere simultaneously, is the approximation we're going to use. All right, let's get back to capacitors now. So capacitors are defined this way. We say that the amount of charge stored on the plate is proportional to the voltage. If I turn up the voltage on the battery, then the capacitor is going to have more charge stored on it. So this proportionality constant is called the capacitance for a particular capacitor. The unit of capacitance is the farad. I think it's named after Michael Faraday, who most of these units are named after physicists who did a lot of research back in the 1800s. So almost everything we talk about in these chapters, these ideas were developed mostly in the 1800s. So that's something to keep in mind, I guess. We're kind of into the physics of the 1800s. Okay, so here's a capacitor. Let's think of it in terms of electric fields. So if I build up a lot of positive charge on one plate and a bunch of negative charge over on another plate, that's going to set up an electric field in the region between the two plates. Now, we've looked at this using Gauss's law. Surprisingly, capacitors are an example of where we use Gauss's law to relate the electric field inside this region. It's given by Q. This is the this epsilon naught. This can be the same thing as 4 pi, 1 over 4 pi k. And so this is going to be 4 pi kq over area. And what can happen then is that we can solve for the electric potential. So back in chapter 23, we showed that the electric potential is given by E times D. Okay, so let's see how we're going to solve for the capacitance here. This is kind of incomplete what they've got. Let's make our own diagram here. So here's the plus charge on this plate, negative charge here. And then using Gauss's law, we can say that E times A is equal to 4 pi kq. And that says that the electric field is given by 4 pi k q over the area for those two plates. So the plates have a certain amount of surface area to them. And this is keeping track of the charge. Now the second item we have to keep track of, and this is the one from chapter 23, is that the electric potential difference, the voltage difference, between the two plates can be related to the electric field times the distance. So the electric field between the two plates is treated as if it's a constant electric field in that region. Now I can substitute in what we solved for the electric field. That was 4 pi k q over A, and then I'll put in the factor of D. Once I've got this expression written, I see that there's a factor of Q here, and there's a factor of V on the other side. What we can do is we can rearrange everything to make the formula look like this. Okay? And so the charge is equal to a bunch of stuff times the voltage. And so I'm going to take this equation and write that down. All the stuff that's inside here, that's what's determining the capacitance of my capacitor. So how much capacitance will we have? Well, it's going to be given by 1 over 4 pi k times the area divided by D. So this is my capacitance formula for a parallel plate capacitor. All right. And that's it. So we're just getting a formula, and then it's also given in terms of epsilon naught. So that's my formula for a capacitor. So let's think about conceptually, what is that telling us? How do I design a capacitor that is able to store a lot of charge? So to get a lot of capacitance, we want to have a big surface area. Well, that makes sense. If I double the surface area, I'll be able to store twice as much charge with the same voltage. So the other item, and this one's a little harder to think about, is the distance between the two plates. So if I can get the distance to get smaller and smaller, if I get these plates closer and closer to each other, I actually get a more concentrated electric field, and we find out that the energy actually well, let's say for right now we're just looking at capacitance. The capacitance goes up, and so I'm actually able to store more charge if I can get those two plates closer to each other. Okay, there's going to be more of a connection between the two plates, and it's going to allow for more charge to be stored in that device. All right, now let's take a look and let's just do a calculation to get an estimate as to how much charge we're actually going to be able to store here. So here we go. Calculate the capacitance of a parallel plate capacitor. That's what we've been looking at. Now this plate is it's not really very square. So what they're saying is this is 20 centimeters by 3 centimeters. So it's kind of like a strip. And then there's a 1 millimeter air gap. Now 1 millimeter might not sound like much, but it turns out that's a pretty big separation for an actual device that we're going to build. Anyway, those are the numbers they've given us. What they want to know then is how much charge will be stored if I attach this to a 12-volt battery. What is the electric field? How much area will I need to have a capacitor with a capacitance of 1 farad for the air gap that we have here? So let's get to work here, right? So here's a picture of my capacitor, and I've got one plate labeled positive, and I got one plate labeled negative. There's a distance of separation. Now in this case, it's not center to center, it is surface to surface. So how much of a separation do I have actually between the plates? And then how much cross-sectional area do I have? I knew that was going to happen. I misread this. So I thought it was 20 by 30 centimeters, but it was 20 by 3. And it looks obvious enough here, but somehow I missed that. So I'm going to go ahead with the 20 by 30. So 20 by 30, I think their intention was to make a long strip, and then the idea is somehow you would wrap this, fold it up somehow. With 20 by 30, I think we're just going to take these plates and just, leave them. But anyway, I ended up with 0.2 times 0.3 meters. That gave 0.0600 meters squared. The distance between was given as 1 millimeter. That also, I'm going to convert over into meters. I'm going to get everything in standard units. This capacitance stuff, hey, it's new. And I've got new units, I've got farads I have to deal with, and I'm just thinking the easiest thing to do is to go back to do everything in standard units. That's going to keep things as simple as possible. All right, so I'm putting in for capacitance, 1 over 4 pi. There is my little k value. And then here I have the area, 0.0600 square meters. And then here is the distance between the two plates. So the distance between the two plates, 0.001. And then I just do the calculations. Now what's going to happen here is I got meter squared here. That's going to cancel meter squared here. I've got this gets a little complicated. I've got newtons over coulombs. If you remember, I can take a newton times a meter, that gives me a joule, divided by a coulombs gives me volts. And so what I'm going to have in terms of units is coulombs per volt. So that's how much charge per electric potential is the way that's going to work. So that's the formula. I've kept everything as standard units. I ended up with 531 times 10 to the minus 12. Now I have intentionally written this as 10 to the minus 12 so that I can convert into some kind of a prefix. So as you guys know, the prefixes like milli, micro, nano, and pico are all going to be factors of 1,000. So milli is 10 to the minus 3, micro is 10 to the minus 6. Oh, here they are right here. Okay, so those are really useful. So when we're working with, when we're working with almost anything in physics, but especially with the circuitry stuff or with the electric fields and whatever, we bring in these prefixes pretty commonly. So I've intentionally written it so that I could use picofarads and I could avoid all the scientific notation. In terms of units, a farad is a coulomb per volt, as we were talking about. And then this is outlined, the volt is a joule per coulomb. That gives me coulomb squared over joules. So a farad is coulomb squared divided by Newton meters. And that's what we have up there in that calculation. So it checks out. The units are farads. And as expected, we got a really, really tiny number, 10 to the minus 12. Well, 10 to the minus 10. And that's because coulombs are a large amount of charge. And so a farad turns out to be an enormous amount of, a farad is an enormous amount of capacitance. So we've figured out the capacitance here. I think that's okay. They wanted us to calculate the charge. So same picture. Ooh, this one's nicely drawn though. I did a better job on this one. That one's drawn pretty well. There's my capacitance. Let's see. Okay, that's later. So this is currently the capacitance. And we're going to attach it to a 12-volt battery. And the charge then is C times V. And that works out to be 6.37 nanocoulombs. See how I went from pico to nano? As soon as this exceeded 1,000, I was able to take out that 1,000 and change a pico to a nano. A pico times 1,000 gives you a nano. So that gives us the amount of charge. Now the electric field, they wanted us to calculate this too, is the voltage divided by the distance. Now, the electric potential, do I have a good picture to bring this back to? Maybe, maybe not. Maybe not. All the way back to here. So here's my capacitor attached to the battery. If I put a voltmeter across the terminals of the battery, it reads 12 volts. That's the difference in electric potential between those two contact points. If I follow these wires around, there's not going to be much voltage drop in the wiring. We're guessing. So we're going to attach this with some, some nice copper wires, very conductive, that's wide enough that the 12-volt difference will be maintained also across those plates. So those plates are also going to have 12 volts across them. So the voltage we're interested in here, 12 volts is being provided by the battery, and since the capacitor is all by itself in that circuit, directly attached to the terminals of the battery, it's going to end up with the a potential of 12 volts. And so I can take that 12 volts and divide through by that distance, and it says that the electric field I'm getting set up is going to be 12,000 newtons per coulomb. That's a pretty substantial electric field that we have between those plates of our capacitor. Okay, so this was the first setup. Then they go, oh my gosh, we just don't have much capacitance here. What would it take to change this from 531 picofarads? What if we use the very same formula, very same distance, D, separation, but instead we want to have a 1 farad capacitor, and you're thinking, oh my gosh, this capacitor is going to be huge. The area would need to be 1.1 10 to the 8th meters. If I make a square capacitor, that's going to give me a capacitor that is 10 kilometers by 10 kilometers? Okay, how am I going to make the capacitor fit tiny dimensions? Because when I look at these capacitors inside electric devices, they're tiny. The capacitors are just tiny devices. And there's a couple things we have to look at here. First of all, the distance between the plates that we're using, a millimeter, that's enormous. In these capacitors, we have a really, really thin conductor layer, a couple of really thin conductor layers, and then a really, really thin insulator between them. So the distance is going to get much smaller by a factor of, I don't know, 100, maybe 1,000. Is that practical? And then the other item that's going to come up is that when we put the insulating material in between, the insulating material actually becomes polarized when we charge the capacitor, and that allows us to store even more charge. So it's kind of a bonus, right? Not only do we need some kind of an insulator between the plates to make sure they don't come into contact with each other, they got to stay separate. The presence of that insulator actually boosts the capacitance by a significant amount. Okay, so yeah, this capacitor we just designed doesn't seem very practical. All right, we can make capacitors that are 1 farad or more. So we do have capacitors that have these properties now, but they're not parallel plate capacitors. Instead, they're activated carbon, which acts as a capacitor at a really tiny scale. So we do have capacitors that are constructed differently to make this all work. All right, let's try some different shapes for these capacitors. Let's do this. Let's get a cylindrical capacitor. We might imagine having a capacitor where instead of having plates that are adjacent to each other, what if we have nested cylinders? What if we have a cylinder inside another cylinder? How would that work? And what we can do then is let's turn the cylinder around so we can look at the electric field. This is kind of what we did last time. When we looked at the parallel plates, we said that, how did we do this? We took the charge, we used Gauss's law to determine what the electric field would be, and then we used electric potential formulas to decide how much electric potential there would be between the two surfaces. So let's try this. The cylindrical capacitor, here's what it looks like. Here's Gauss's law. We're going to go from inner radius of A to outer radius of B. Here is Gauss's law here. Remember, for cylindrical symmetry, when we integrate through, the area we get is 2 pi r times L. And that gives us an electric field between the two cylinders of 2kq over L, 1 over r. So that tells us how the electric field varies, and as would be expected, the electric field is going to be more concentrated, it's going to be larger, near the smaller values of r, and then as we get to larger values of r, the electric field drops off. Now what that means is that when we're doing the voltage calculations, we're going to have to integrate over the electric fields. Now, I don't think you guys are going to need any of this integration. This is mostly just to show you where some of the formulas are coming from. But in any case, it should be a fairly straightforward integration. 1 over r integrates out to be the natural logarithm. And since we have limits between a and b, the inner radius and the outer radius, what we're coming up with is a formula for the electric potential difference from the inner radius to the outer radius. So V then is going to be 2kq over L, natural log of B over A, where those are the two radiuses. And once again, what we've done is we've ended up with a formula that has Q built into it, and then on the other side it's actually a voltage formula, or electric potential. When we solve that formula for Q, and then isolate the V, everything else is capacitance. So everything else in that formula is telling us what the capacitance will be for a cylindrical capacitor. So what we're finding here is, let's see, this capacitor is going to depend proportionally on length. And you go, well, of course, that's going to make sense. If we make the capacitor twice as long, we can store twice as much charge. So the capacitance we're finding out depends on length. And then it also depends on B over A, the ratio. So how many times bigger is B compared with A? And then we end up taking the logarithm of that. So once again, it's going to depend on the shape of the capacitor. In this case, it's a cylinder. And it's going to depend on separation. So the separation between the plates is actually built into that ratio. B over A is a ratio that tells us how close one of the plates is to the other one. All right, so yeah, we can even derive a formula for a cylindrical capacitor. Oh my gosh, they're going to have us do a sphere. I knew that was coming, right? Because what we're really doing here is we're using chapter 22, Gauss's law, to go through and derive all these capacitor formulas. Fine, we can do that. So once again, we've got two radiuses. I've got a distance between the inner surface and the outer surface with this region. There's going to be an electric field set up. When we connect this capacitor, somehow the inner spherical surface is going to get connected to one of the battery terminals and the outer surface to the other one. And that's the picture of how the charges will be arranged. Now, let's see, what were the two steps we've been using? First step was solve for E using Gauss's law, solve for E in terms of Q. Once we solve for E, go back and solve for the voltage difference between the inner and the outer surface. So I'm thinking we're going to do the same thing. Inner radius of A, outer radius of B. We're going to introduce a Gaussian surface in between that region. Now the Gaussian surface is going to need to have any value of little r between A and B. So it can be any value. In fact, when we integrate here, we're going to have to include all those possible values. So here's Gauss's law, and it's a spherical shape. Now, one warning I want to put out there is that when you look on the end here, when you look at that diagram that we drew, is that a sphere or a cylinder? And I can't tell. If I do an end view of a cylinder, it looks the very same thing as a cross-section of a sphere. So read the problems carefully. Sometimes students are asked to answer questions about a cylinder and they think it's a sphere, or about a sphere and they think it's a cylinder. And so read the problems. Make sure that you're answering the right problem. So this is a sphere, and so the surface area is 4 pi r squared. And the electric field then, solving this, is kq over little r squared. That's the electric field inside here. Now, we've got the q and the electric field related. Now what we want to do is come up with a formula for the electric potential. We want to be able to solve for the electric potential difference, one side to the other. We want to introduce the voltage into our formula. So I can take the electric field formula, substitute that in. This time there is an r squared. So my integral now is dr over r squared. That integrates out to be minus kq over r, evaluated from a to b. That's the same thing. To get rid of the minus sign here, I can evaluate from b to a. If I reverse the limits of integration, that changes the overall sign on that expression. And so the potential difference here is kq, 1 over a, minus 1 over b. Or kq, b minus a over ab. Once again, we're going to take that equation and solve it for q. So we got the electric field in terms of q. We use the electric field to solve for the potential. When we get the potential, potential is a function of q. We take that formula, solve it for q, and then we look and observe what parts of that is the capacitance. And the capacitance here is going to be given by AB divided by B minus A times 1 over K. So every one of these formulas has a 1 over K in it. And then it has dimensions. Now in this case, it's a little trickier because I've got two radiuses. I don't have a length dimension in here so much. I have two radiuses, and it does turn out that this is the separation distance. So B minus A, hey, that's the distance between the two plates. And AB turns out to be kind of like an area, or proportional to the area, let's say. In any case, for a spherical capacitor, that's the formula we're getting. So that tells us how much capacitance a capacitor would be if we built it with this geometry. Okay, so here's one more. I wasn't counting on this one. So what we could also do is this. What if I have two wires? So I've built an electric device, some type of an electric device, and it has two wires running in it. Or, similarly, what if it's just an electric cord that I plug into the wall? You know, maybe I have an electric cord, one of those where the cord on the electric appliance has two conductors that are kind of joined together. How much capacitance is there in those two wires if the wires happen to build up a certain amount of charge? Now, typically when we're operating devices, the charges on the wires are negligibly small. But if I did have two very long, straight, parallel wires, each of radius r, carrying uniform charges of plus q and minus q, separated by some distance d, center to center, what would the capacitance look like? And the first thing I'm going to do here is say, okay, what would the electric field look like between these two wires? So this wire has, for whatever reason, it's acquired a positive charge. This wire has acquired a negative charge. And what I've done is I've shown where the equal potentials are. So we would need some way to determine what is the electric field between those two wires, and then use the calculate using the voltage formulas to how much electric potential difference is there from one side to the other. Okay, so I'm actually doing this. Okay, so anyway, these are not plates, these are wires, and what I'm going to do is I'm going to follow that central line. So this example again is a bit tricky. So the wires here are running parallel into the board and out of the board. This is where I'm actually going to follow the electric field line, and I'm hoping that's going to give me the easiest path to follow. So let's see if that actually works. What we'll do is we'll go back and remember with Gauss's law, we had said that the electric field surrounding a very long charged stick, so if I think of this as just some sticks, conducting sticks that I'm going to make into a capacitor. So I have a long wire here and a long wire here. The electric field is going to be kq over L times 1 over R. For each wire, and this needs, oh I see, Q over L is lambda, right. And so what we can say then is that if I look at the electric field at any location along here, it's going to be the combination of the electric field due to this wire plus the electric field due to this wire. Now what I've done is I've introduced a coordinate system where x equals 0 runs along the center point between the two wires, and that says that the distance little r that I am away from this wire is going to be a plus x, and the distance from this wire is going to be a minus x. So I'm going to take the electric field due to the positive wire and the electric field due to the negative wire. Now they're both in the same direction. So I am going to get an electric field added together in that direction. I'm going to get kq over L times 1 over a plus x. If I have a point here, point A, that's located at distance a plus x. And then for the other wire, it's a minus x. And then I'm just going to add those together algebraically. So it becomes kq over L. I'm going to get a factor of a minus x, or a term of a minus x, plus a term of a plus x, over a common denominator, a squared minus x squared. And the x's cancel out. I'm going to get an electric field that is kq over L, 2a over a squared minus x squared. So this time we didn't use Gauss's law. We went back to chapter 21 and used, well, I guess we did use Gauss's law because this is really kind of where that electric field formula is coming from. So let's say, yeah, it's from chapter 22 and we're thinking of a couple of cylinders and using those to get the electric fields and then combining those together. Now the voltage difference, or the electric potential difference, will come from integrating that expression, and that's complicated, that last expression that we have down here. I looked it up, and it said that this integral is 1 over 2a natural log a plus x over a minus x. Plugged that back in, carried out the integration, evaluated it between minus a, and ended up with a voltage difference between the two that is given by this expression. All right. Now, what I'm finding here is that if we're integrating from all the way from minus x to positive x, I'm going to end up with some zeros in this formula. So the calculations are going to get out of control. How did that happen? Well, let's go back and take a look at this. What I did was I neglected the actual width of the wire. If I allow the wire to be infinitesimally narrow, then I'm going to have electric fields that are infinitely large as I do that. So I was hoping to be able to get away with not including the thickness of the wire, but it turns out I couldn't. Mathematically, sometimes these things catch up with us. And so I couldn't use that as an approximation, so I did need to go back in. I went back in. See here, I'm going to run into issues of infinities showing up with the limits that I have. So I went back and reevaluated that integration, and this time I took it from minus a minus r to positive a minus r. I went from the edge of one of the sticks to the edge of the other stick. And when I did that, I was able to get a formula that worked. And so I got these two natural logarithms. I followed the rules for logarithms to combine those two into one, and ended up with this formula. So the formula that we end up with here turns out to be here is the Q that we ended up with. There is the voltage that we've calculated. So for two wires, we've got that for the capacitance. And so so we do have the possibility that if parallel wires become charged, if we end up storing charge on those, that there could be communication taking place between the two wires. We could have crosstalk. If I've got information transmitting along some of these wires, I want to make sure that the wires remain independent. That when I send a signal down one of the wires, it doesn't generate another signal going down an adjacent wire. So this type of capacitance issue, kind of built into the wiring, is something that, you know, electrical engineers have to keep track of these sorts of issues. Okay, I'm thinking that's probably a good place to take a break for today. We're going to come back after break and start looking at multiple capacitors. And so I'm going to stop right there. And again, we'll come back and look at some more capacitance.